Okay, and so now we've done linear interpolation, the simplest kind of interpolation. Next, we're going to up the ante. We're going to go to polynomial interpolation. So in the same way that you can find a line between any 2 points, right? So you can do this interpolation between 2 points in a polynomial. You can find a quadratic polynomial, order 2 polynomial, between any 3 points. Or you can find a cubic polynomial, order 3, between any 4 points, and so on and so forth, right? And so the next type of interpolation we're going to look at is how do you find a polynomial between any, an order n polynomial between any n plus 1 points. This is called Lagrange interpolation. In practice, what we'll do is we'll do either quadratic, and this is find a quadratic equation between each set of 3 points, or cubic, so find a cubic equation between each set of 4 points. And in practice, we don't go any higher than that. So quadratic interpolation, cubic interpolation is kind of as far as we go. And so what you'll do if you want to do quadratic interpolation, just like you did with linear, you're going to split your curve up into sets of 3 points. So like x1, x2, x3, then x3, x4, x5, x5, x6, x7, and you're going to find a quadratic polynomial between each of those sets of points, just like we found a linear, and you'll get a piecewise quadratic equation or a piecewise cubic equation. Okay? Now in practice, we don't go any higher than order 3 because the polynomials start to act strangely. So quadratic polynomial, or quartic polynomials rather, or quintics even more so, can blow up very, very quickly because you've got an x to the 4th power or an x to the 5th power, and those numbers get really, really large, and so they can behave very strangely. Okay? So in practice, just like we did with linear, we're going to find a quadratic equation between sets of 3 points, cubic equation between sets of 4 points. Okay? The technique we use to find a polynomial between n plus 1 points is the same regardless of the polynomial. Okay, and so this is an extension of what we did with linear polynomials, where we're kind of building, rather than one slope, we kind of have multiple slopes now. We have multiple points that we're plugging in. And this is what's called the Lagrange polynomial. So, if we want to find an order n polynomial through x1, y1, x2, y2, all the way up to x n plus 1, y n plus 1, right? So if we want to find an order n polynomial, we need n plus 1 points. We need one more point than the number of polynomials. So like for a quadratic, we would need 3 points to define a quadratic polynomial. What we're going to do is we're going to take these points and we're going to create the Lagrange polynomial. Okay? And so what the Lagrange polynomial is it's going to be defined as y equals f1 of x times y1 plus f2 of x times y2 all the way up to plus 1 of x times yn plus 1. Okay? Where these y1, y2 up through yn plus 1, those are your data points yn, yi from each of these. Where this gets interesting and complicated is in defining these fi. Okay? So fi of x and I'm going to write down this definition. It looks very complicated. Okay, I will warn you, it's going to look very complicated, but I'm going to explain to you how you do it, and it's actually not that bad. Okay, so on the top, we're going to have a bunch of terms that have x minus each value. So x minus x1, each value of x minus x2. So here, these x1, x2, those are your data points. X is your variable, okay? So x minus x1, x minus x2, all the way up to x minus xi minus 1, x minus xi plus 1, and then so on to the last one, x minus xn plus 1. Okay? So what I've got here is I've got an x minus xi for every single term except the one that matches this index. So we're skipping one of them. Okay? So we've got x minus x1, x minus x2, x minus xi minus 1, and then we skip right ahead to x minus xi plus 1. Okay? So we skip over that xi term. Okay? Similarly, in the denominator, this is actually basically the same, except we replace x with xi. So xi minus x1, xi minus x2, xi minus xi minus 1, xi minus xi plus 1, and xi minus xn plus 1. Okay? So this is a lot to process, right? But the idea here is that on the top, we've got x minus each of the x values, each of the x data values. On the bottom, we've got xi minus each of the x data values, except for the one that matches our coefficient on this. Okay? So this formula looks complicated, but in practice, it's not that bad to do, especially when you're just doing a quadratic or a cubic interpolation. It's actually not so bad. So let me show you with the data points how this works. So we've got those 3 data points that we just talked about. So I'm going to erase all of this. Make sure you write it down. You can go back and pause and write that down if you need it. So let's find a quadratic equation through the points 0, 2, 1, 3, and 2, 5. Okay? So this is going to be kind of the equation is going to be y is going to be our f1 of x times 2 times the first y1, f2 of x times 3, and f3 of x times 5. Okay? Where f1 is going to be the one where we skip the x value from this one, f2 is going to be the one where we skip this one, and f3 is the one where we skip this one. Okay? So if we write this down, so let's figure out f1 of x first. So on the top, we're going to have x minus, we skip x1, we don't do that one, go right to x2. So x minus x2, x minus x3. Okay? In the denominator, we're going to have x1 minus x2, x1 minus x3. Okay, that's our f1 of x. So we've got an x minus xi term for everything but the first one. We've got an x1 minus xi term for everything but the first one. okay? And that gets multiplied by 2. And I'm going to explain the theory here in a minute, where this comes from and why this polynomial works, once I've got it written down, because then I think it's very easy to see kind of why this works. Okay? So that's our first term. F2, we're going to skip this one. So that's x minus 0, x minus 2 over 1 minus 0, 1 minus 2 times 3. So in F2, we skip over that point. We do x minus x0, x minus x2, x1 minus x0, x1 minus x2. Okay? And then the last one, we're going to get, we're going to skip over this one. So x minus 0, x minus 1 over 2 minus 0, 2 minus 1 times 5. Okay? So you can simplify this down. There's a lot of arithmetic you can do in algebra. You can work this out. So I'm not necessarily going to go through all of that. If you simplify down the algebra, you can reduce this down to kind of a classic polynomial like we would expect. So if you write this down, you can go through, reduce this polynomial down, multiply everything out, get the coefficient down here. Notice that the denominators are all integers, so this isn't actually that bad. Okay? So we end up getting 1/2 x squared plus 1/2 x plus 2. Okay? That ends up being our equation. And if you look at that equation, that actually goes through all of these points. So if you plug in x equals 0, x equals 0, x equals 0, you get 2. Plug in x equals 1, you get 1/2 plus 1/2 plus 2. That's 3. Plug in x equals 2, you get 1/2 of 4, which is 2. 1/2 of 2, which is 1. So 2 plus 1 plus 2 gives you 5. This polynomial goes through all 3 of these points. Okay? So let me talk about the theory of why that happens. So if you look at this, what's going to happen if you plug in x equals 0 to this unsimplified polynomial? Well, if you plug in x equals 0 to this first term, you get 0 minus 1 times 0 minus 2 over 0 minus 1 times 0 minus 2. This whole thing becomes 1, becomes a constant 1. Okay? So that term just becomes 1. We get 1 times 2. The other two terms become 0. Okay? So if you plug in x equals 0 here, you're going to get 0 minus 0, which gives you a 0 here. Okay? And so this whole thing gets zeroed out. Similarly here, you've got 0 minus 0. This whole thing gets zeroed out. So what happens in each of these terms is that if you plug in the corresponding xi, this one becomes 1. So we get 1 times 2. That gives us exactly the value that we expect, the y1 value. The other terms all become 0 and drop off completely. Okay? Similarly, if you plugged in x equals 1, this one would become 0, this one would become 0, and we'd just be left with this, which would become 1, multiplied by 3 gives us 3. Okay? So that's why this Lagrange polynomial works. Now, if you want to do something more complicated, certainly if you're doing quadratic interpolation, you would have multiple of these, right? So you would do this first for the first 3 points, and then for the next 3 points, and so on. And I'll do an example like that in the next video.